are both our sites, and what you can see is that there is, so the blue area is the area where we find that bioclimatically, these areas are similar to our two study sites. We also looked at the similarity in terms of the ALS data. So we used principal component analysis to look at this. And so we found that, so this is first on the left, in the middle is Slave Lake. And we found that the contributions of our ALS metrics that we calculated were very similar compared to both. And the patterns, when we look at these, at the two principal component analysis, were very similar too for both of these areas. Also, when we look at our data in coordination space on the right there, we see that there's a lot of overlap between these data points from both areas. So then, in terms of the prediction results that we have. So on the bottom is our percent mean square error. Here's our bias. We have our basal area, our gross total volume, Lorey's height, and then quadratic mean diameter. We have our parametric model on the top, and the random forest model on the bottom. And the different colors represent the different scenarios that we ran. So not to go over all of these, of the results or what we can derive from this, but our main results were that our Lorey's height, not surprisingly, was our best model that we could transfer, followed by quadratic mean diameter. And in these two, so basal area and total volume, we see something else happening, and we'll talk about that in the next slide. But first, the general things that we can take away from our models was that our best transferred models fell within 5% of the relative mean square error, but increased up to 10% in terms of relative bias compared to our local models. And those were always our scenario 2 or our scenario 3, and those are multi-site models, so where we combine data from the target site and from the other site, so where we combined these two data sources. And our worst transfer models, those were always our scenario 1, so those are the green ones, and you can see that they're always much further out, so much higher mean square error and much higher or lower, like further from 0 in terms of bias. And we saw there up to 23% relative mean square error and up to 30% bias when compared to our local models. So what is happening in our volume predictions? So here is our local model for Hearst and for Slave Lake. These are our scenario 1, so our single sites, and then on the right-hand side is our scenario 2, so multi-sites. So what we saw was happening in Hearst is that we're over-predicting, so even up to the extent that we saw predictions that were beyond what we saw in the field, and not only in the random forest models, but also in the OLS models. And we saw the opposite in Slave Lake. And when we combined some of the Hearst model data in the Hearst models, or then we transferred to the Hearst, and we combined some of the Slave Lake data in these models that were transported or transferred to Slave Lake, we see that we get closer to this one-to-one line, still a little bit more off than our local models. And I included here the forest type, so CL is lowland conifers, then upland conifers, deciduous, mixedwood, and pines, and we see that it's happening over all the forest types. So why would this be? So if we look at the plot data, we see that these are the distributions of the plot data for total volume. We see that we have a much longer tail, so we have higher volume values in Slave Lake compared to Hearst. Also, when we look at, so on the bottom is Lorey's height, our plots are colored by quadratic mean diameter, And then on the left-hand side is gross global volume. We see that when we have plots with a higher Lorey's height, so within the 20 and 30 meters, we see that in Slave Lake, some of these plots pack a lot more volume than that we see in Hearst. So would that be related, or is that related to this bioclimatic gradient? So when we look at some of those attributes, so we looked at growing degree days, average daily temperature, average precipitation, and elevation, and we do see that there is differences there, and we do know from the literature that volume is impacted by those bioclimatic variables. So then in conclusion, what we found in our research was that prediction accuracy of our method or of our models varied by modeling approach, by attribute, and by site. So we don't really see a clear pattern. It's much more variable than that. We do see that if you add some data in of the target site, that improves model performance. And in our case, the total volume data showed us the example that differences between attributes and differences in standing conditions between those forests, due to, in our case, the variation in bioclimatic conditions, represents a challenge when you want to transfer these models. And so in terms of operational forest management, there is this trade-off between the tolerance for estimated accuracy that you have to take into against the cost of acquiring additional field costs. So when the models be acceptable from an operational perspective, that's a trade-off that you have to consider. Yeah, and then I want to thank, this research was done within the layer, so the universities, but also the industrial partners that were part of this project. They were just as important. They had the data and they helped with the field data. So